Today, in this video, we'll be introducing the concept of chemical equilibrium. And at the end of the video, your objective is to be able to define what irreversible reaction is, as well as to describe the conditions that must be met for a chemical equilibrium. Now, let's first discuss the concept of irreversible and reversible reactions. Irreversible or complete reactions are those that proceed in one direction only or in the forward direction. So far, in all your grade 7 and 8 discussions in chemistry, you dealt with irreversible reactions. So, for example, you have the combustion of methane in the presence of oxygen to produce carbon dioxide and water. Once the reactants have all been converted into products, those products can no longer reform back into the reactants. On the other hand, a reversible or incomplete reaction is a reaction that proceeds in both directions at the same time. If you can recall in our lesson about weak electrolytes, we have discussed that weak electrolytes are able to produce some ions in the solution. However, some of those ions can also reform back into its molecular form. A specific example of which is acetic acid, which can dissociate into hydrogen and acetate ions, but those products or those ions can also recombine back to form the molecular form of the acetic acid. Some textbooks would write the double-headed arrow as this one, while others would write it as in this form. So all of these are double-headed arrows which indicate reversible reactions. Now, let's define what equilibrium is. And intuitively, we can define this as a state of balance. And you have been introduced to mechanical equilibrium in your physics class, just how Thanos is balancing this object here. In chemistry, we also have this idea of thermal equilibrium, wherein if you let two objects of different temperatures touch each other, there will come a time where the two objects would have one temperature, and thus they are termed to be in thermal equilibrium. In biology, you were also introduced to, sorry for this typographical error, this should be homeostasis. Okay, kindly correct in your notes. So this should be homeostasis. And if you can recall, homeostasis is the natural response of an organism to achieve balance. For example, when you are exercising or after exercising, your body is feeling hot and the body's natural response would be to sweat in an effort to cool down the body. So you all have those ideas about equilibrium in physics, chemistry, and in biology. Now let's go to the reversible reactions in thermal equilibrium. Okay, so we'll be watching a video and you have to note that we have this following analogies. So you have two tubs, one with water, and you should relate the amount of water in the tub as the amount of reactant, the amount of product, and later he'll be showing you a beaker, okay? So when he shows you the beaker, you would relate the amount of water in the beaker to the reaction rate. So initially, we have reactants only, and we don't have products yet. Okay, so let's watch the demonstration. Okay, so now he's showing the beaker. And again, the beakers represents the amount of water in the beaker rather represents the rate of the reaction. As you can see here, since the reactant side only has the water, then the reaction rate of the forward reaction would be faster initially. Okay? But after some time, as more water is added or as more amount of products are added now to the other side, then the rate of the reverse reaction, which is product reactant, would then increase as well. Okay, so this continues on for some time, and we can relate that to a chemical reaction that is trying to achieve chemical equilibrium. And we do this back and forth movement up until, okay, let's wait for the close up there. Okay, up until reach a point when the amount of the water in the beaker are already equal. Okay, so when that happens, okay, when the rate of the forward and the reverse reactions are already equal, then we can say that the reversible reaction has already achieved thermal equilibrium. So once the reaction has achieved thermal equilibrium, we can continue the exercise throughout the day. We can even continue that theoretically throughout the week. But the amount of water in each tub or the amount of reactant and product would no longer change, even though you continually scoop the water in and out in the two tubs. For this scenario, we can say that after some time, the amount of reactants and products have become equal, okay? And this is understandable since we have two equally sized beakers. If we look at the rate of the reaction, we could see that initially it was the forward rate which was greater and the reverse rate was slow at the start. However, it came a point, okay, when the amount of water in the beaker are already equal. It came a point in the reaction wherein the forward and reverse rate have already been equal. And we say that that's thermal, no, that's chemical equilibrium. Okay, let's go to the second analogy, okay, or second scenario rather. So the man will be returning the water to the reactant side. And now he'll be using two different sizes of beakers. For the forward reaction, he'll be using a big beaker and a small beaker for the reverse reaction. Okay, you can pause this video right here and try to predict which would end up with the greater amount. Is it the reactants or the product? So he's continually scooping this just as what he did in the previous scenario, okay? And I hope you guessed right, wherein after some time, you'll have more products and less reactants. He's trying to compare the amount, okay? So the smaller beaker has about 140 ml of water, whereas the other beaker has about a little less over 140. So the demonstrator is not yet satisfied, so he's continuing this, okay, to to show you that they're not equal yet. Okay, you can also pause the video and predict whether the amount of water inside the beaker would be equal after some time. Will the reactants run out? Okay. There's a zoom in there, and you can see that the water now in each side was about 150 ml for the small and the bigger beakers. Okay, So even though we started with different sized beakers, there came a time where the rate of the reaction were equal. Okay, but look at the amounts. Okay, so for this second scenario, we started with initial amounts, same as with scenario one, okay? But we ended up with greater amounts of products and lesser amount of reactants. However, for the rate, it's still the same, okay? After some time, even though we had a bigger beaker for the forward reaction, the forward and reverse rates became equal after some time, okay? Now, in this particular scenario, we can associate this to a reaction where the products are favored because they are in greater quantity. Or we could also say the forward reaction is favored. Okay, we can also flip the scenario wherein we use a where we'll end up with this amount, okay, at equilibrium, and we can predict that maybe okay he used a bigger beaker in the product side and a smaller beaker in the reactant side. Okay. Now, for this particular scenario 3, okay, please select scenario 3, the reactants ended up in greater quantity compared to the product. But again, if you do this exercise even practically, you'll still end up with this graph for the rate, wherein the forward and reverse rates are equal. Okay. And for this scenario, we say that the reactants are favored or the backward reaction is favored. For all of these scenarios, we can summarize them as this. We say that we have achieved chemical equilibrium when we observe that there is no longer a change in the amount or concentration of reactants and products with time, as well as the the rates of the forward and the reverse reactions are equal. Okay, so at chemical equilibrium, in a reversible reaction, both reactants and products are present. Also, chemical equilibrium is said to be a dynamic process. Dynamic in a sense wherein we don't see a macroscopic change, just like what we saw in the video, wherein the man could continue scooping water and swapping them between the tubs, but the amount of the reactant and product would no longer change. So he can continue with the reaction backward and forward, but we won't see a change anymore macroscopically in terms of concentration. But we know the reactions didn't stop. There's still this forward and reverse reaction happening simultaneously, continuously. Okay, now we go into the types of chemical equilibrium, and this is quite easy for you. Okay, so we say that a chemical equilibrium is homogeneous when all the components, reactants, and products are of the same phase. And we say that a chemical equilibrium is heterogeneous if it involves more than one phase. Like in this diagram or in this reaction here, you can see you have a solid substance converting into ionic form. So that ends the video.